So till now we were dealing with the problems which can be solved by using the rules of series circuits and parallel circuits. But from now we will be dealing with the problems or complex circuits which cannot be easily solved by using the rules of series circuits and parallel circuits. For that we are defining another rule, which is the symmetry rules. So we can call this a symmetry rule as a trick to solve any equivalent resistance. So basically, what is a symmetry? So from the mathematical point of view, we can say that if one side of the plane is the mirror image of the other side, so we can say that there exists a symmetry in that plane. Now if we have a complex circuit and we are asked to find out the equivalent resistance between 2 points in that circuit, let's say point A and point B. We are asked to find out the equivalent resistance between these 2 points. Now if we draw a horizontal line to join these 2 points, and we draw another line which bisects this horizontal line by an angle of 90 degrees. Now if one side of this plane is the mirror image of the other side, then we can say that there exists a symmetry in this plane or in this complex circuit. So we can use the rules of a symmetry to solve that kind of complex circuits. Now there are two types of symmetry basically. The one is called the vertical symmetry and the other one is called the horizontal symmetry. So let's discuss first the vertical symmetry briefly. So basically, what is a vertical symmetry? So as the name suggested here, that if we draw a vertical line that bisects the horizontal line between any 2 points, and if there exists a symmetry, or if one side of this plane is the mirror image of the other side, then we can say that there exists a vertical symmetry. Or by mathematical point of view, we can say that symmetry about the y-axis is basically called the vertical symmetry. Now for the complex circuit, there are a rule which we use to solve any complex circuit, which states that the current will be the same on either side of the vertical symmetry. So this point will be easy for you after some time. Now let's take an example to understand the vertical symmetry, or sometimes we can call this vertical symmetry as in mirror symmetry, in which we are asked to find out the equivalent resistance between point A and point B. So we have given a bridge type network. So if you look into this network, so this network cannot be directly solved by using the rules of series circuits and parallel circuits. So if we can find out the vertical symmetry in this complex circuit, so then we can solve this circuit easily. So if we join these 2 points by using a horizontal line, and if we draw a vertical line which bisects the horizontal line by 90 degrees at this point, so if you look into this circuit briefly, then you would see that this side of the circuit is the mirror image of this side, because the point A is the mirror image of point B, and these 2 resistors are the mirror image of these 2 resistors. So we can say that there exists a vertical line of symmetry. So if we use this rule, the current will be the same on either side of the vertical symmetry. So by the same current, we means that if there exists current I1 through this resistor and current I2, let's say through this resistor, so the current I1 will also be flowing through this resistor. I1 will flowing through this resistor and I2 will be flowing through this resistor. So we can say that this side of the circuit is the mirror image of this side. So as a result, there will be no current through this resistor. So we can remove this resistor from our analysis, because if there is no current through this resistor, there will be no potential across this resistor. So we can simply remove this resistor to simplify our circuit. Now if you remove this resistor from this circuit, then the analysis will be easy for you. The analysis will become easy for you because there is no current through this resistor. Now if you look into this network again, then you will see that there exists a same current through these 2 resistors, and there exists a same current through these 2 resistors. So these 2 resistors are in series, and these 2 resistors will also be in series. So let's redraw this network again. These 2 resistors R and R are in series, and these 2 resistors are also in series, because the current through these two resistors is the same. the current through these two resistors is the same. There exists current I1 through these two resistors and current I2 through these two resistors. So as these two resistors are in series, so the equivalent of these two resistors is 2R, and the equivalent of these two resistors will also be 2R. So the equivalent of these two resistors is 2R, and the equivalent of the bottom resistors is also 2R. This is point A and this is point B. Now the equivalent resistance of these two resistors will be 1 divided by R equivalent is equals to 1 divided by 2R plus 1 divided by 2R, because these two resistors are sharing the same 2 points, so these two resistors are in parallel. So after calculating this, you will get R equivalent is equals to R. So the equivalent resistance between these 2 points A and B is R. Now let's move towards another point, which is the horizontal symmetry. So basically, what is a horizontal symmetry? So as the name suggested here, the symmetry about the x-axis is basically called the horizontal symmetry. Now if we have a complex circuit and we are asked to find out the equivalent resistance between point A and point B, point A and point B. Now if we draw a line which join these 2 points, draw a horizontal line which can join these 2 points A and B. Now if the upper side of this network is the mirror image of the lower side, then we can say that there exists horizontal symmetry in this circuit. So we can use the rule of horizontal symmetry here to find out the equivalent resistance between point A and point B. Now a setup rule which we use to find out the equivalent resistance across any horizontal symmetry is the voltage will be the same at the symmetry points. So this is basically the rule which we use to solve any complex circuit in which a horizontal symmetry exists, and this horizontal symmetry is sometimes called the folding symmetry. So both the names are used. Now to understand the horizontal symmetry in a more brief way, let's take an example in which we are asked to find out the equivalent resistance between point A and B by using the rules of horizontal symmetry. So first of all, we need to draw a horizontal line between point A and point B. Now if you analyze this network again, then you will see that the lower side is the mirror image of the upper side, because the number of resistors available at the lower side is equals to the number of resistors available at the upper side. And at both of these sides, the resistors are connected at the same points, and the resistance value of these resistors are also the same. So by using this point, the voltage will be the same at the symmetry points. So we can say that if the voltage across this point is V1 and the voltage across this point is V2, the voltage across this point is V3. So we can easily say that the voltage across this point will also be V2, because there exists a horizontal or a folding symmetry across this x-axis or this horizontal plane. Now let's simplify this network to understand this point in a more brief way. So the potential at this point is the same as the potential at this point, so there will be no current through this resistor. So there is no potential difference across this resistor. So as a result, there will be no current through this resistor. So we can remove this resistor from our analysis. Now let's redraw this network in a more simpler way to solve this network. Now let's say this point represents V1, this point represents V2, and this point represents V3. So between V1 and V2, we have a resistor R. Between V1 and V2, we have resistor R. And between V1 and V2, again we have a resistor R. Between V1 and V2, we have a resistor R, because these 2 points are at the same potential. Now in between V2 and V3, we have a resistor R. And in between V2 and V3, we again have a resistor R. And these are basically point A and this is point B. Now if you look into this network, then you will see that these 2 resistors are in parallel and these 2 resistors are also in parallel, because these 2 resistors and these 2 resistors are sharing the same 2 points. So the equivalent resistance 1 divided by R equivalent will be equals to 1 divided by R plus 1 divided by R. So R equivalent from this equation will be equals to R divided by 2. R divided by 2. So we can replace these two resistors and these two resistors by its equivalent resistance. So the equivalent resistance between point A and B. So the equivalent resistance of these two resistors is, let's say, this one, which is R divided by 2. And the equivalent of these two resistors is this one, which is R divided by 2. And this is point B. Now these two resistors are in series, so the equivalent of these two resistors will be equals to R divided by 2 plus R divided by 2. So the equivalent resistance of these two resistors will be R. So the equivalent resistance between point A and B is R, which is the same as we found out for the vertical symmetry. So in today's video lecture, we discussed a rule called a symmetry rule, and we also discussed two types of symmetries. The one is vertical symmetry and the other one is the horizontal or folding symmetry. And in the upcoming video lecture, we will be discussing more complex problems which is related to the symmetries. So see you in the next one.